Now that we've talked a little bit about how to determine if a solution exists and if it's unique for an initial value problem, I want to take kind of a sidestep today and talk about what happens if we have solution curves without a solution. What can we do? So this is when the answer to that "does a solution exist" question is no. What can we do? What's our next step? So if there is no solution with that specific initial condition, we might wonder, how do solution curves actually behave near that specific point that was our initial condition? Or how does the solution behave as x approaches infinity? What does this differential equation look like? What do the solution curves look like? Now, in order to explore this, we're going to look at it graphically first. And when we think about graphs and derivatives, we need to remember that a derivative, dy dx, of a differential function, y equals y of x, gives slopes of tangent lines at points on its graph. So if I have a first-order differential equation, dy dx equals f of xy, some function in xy, with some solution y equals y of x. Now, that means that that function, f of xy, that's equal to the derivative, that function is going to represent slopes or rates of change. So we call it a slope function or a rate function. And in fact, if I plug in values for x and y, I can come up with a whole bunch of little line segments that would be tangent lines to my solution function at each of the xy values that I plug in. Each one of those little tangent line segments that I create is called a lineal element. If we take a whole bunch of different values for x and y over some rectangular region, and we find all of the lineal elements, and we put them together on a graph, what we've done is created something called a direction field or a slope field. So we're going to go through two examples really quick here. The first is going to be creating this direction field or slope field. And the second one will be, if we're given a slope field or direction field, how do we read it? What can we do with it? So let's take a look at creating a direction field or slope field. If I'm given the differential equation, y prime equals y minus x, I can take x and y values and plug them in to y minus x, and that's going to give me the slopes, the derivative, at that xy point that I plugged in. So let's start at the origin. So if I plug in 0 for x and 0 for y, then I get 0 minus 0, or 0. So I know the slope there is 0. So I make a little line segment with slope 0 at the point 0, 0. Now, if I plug in 1 and 1, 1 for x and 1 for y, then I'll get 1 minus 1. So I'll get at the point 1, 1, the slope is also 0. And I can notice for this equation, if x and y are equal to each other, since I'm subtracting them, it's always going to be 0. So I know that my slope is always 0 when x equals y. So at the point 2, 2, I'll also have a slope of 0. At negative 1, I'll have a slope of 0. And at negative 2, I'll have a slope of 0. Now let's move on to another point that I haven't found anything for. So let's look at the point 1, 0. That is 1 for x and 0 for y. If I plug in 0 for y and 1 for x, then I get 0 minus 1, or a slope of negative 1. So I sketch a little line segment that has a slope of negative 1 at that point, 1, 0. Then I'm going to look at the point 2, 1. So x is 2, y is 1. So I'll get 1 minus 2, or negative 1, at the point 2, 1 as well. And in fact, I can notice that whenever x is 1 greater than y, then my slope is going to be -1. So this also occurs when x is 0 and y is -1, and when x is -1 and y is -2. Now let's go to a new point that hasn't been graphed yet. Let's look at x is 1, y is -1. When I plug that in, I get -1 minus 1 for a slope of -2. So I sketch a line segment there that has a slope of -2. Now if x is 2 and y is 0, I also get a slope of -2. And then whenever x is 2 greater than y, so when x is 0, y is -2, I get a slope of -2. Then let's take a look at the point 2, -1. So if x is 2, y is -1, I get -1 minus 2, or -3 as a slope. So I sketch in a slope of -3. And I also get a slope of -3 when x is 1 and y is -2. And then finally, to finish out this quadrant 2 space, I get x is 2, y is -2, so I get -2 minus 2 for a slope of -4. And that shows me kind of the shape of solution curves for that part. Now let's go up above those 0 slopes and see what's happening. So what happens when y is 1 and x is 0? Well, I get a slope of +1. So I sketch in a little line segment with slope +1. When x is 1 and y is 2, I also get a slope of +1. So I sketch that in. Whenever y is 1 greater than x, I'm going to get a slope of +1. So it happens at x is -1 and y is 0. It also happens when x is -2 and y is -1. Now, if I move on to a new point, say, let's look at when y is 2 and x is 0. So when y is 2 and x is 0, I get a slope of 2 minus 0, or 2, +2. So I'm going to sketch in a line segment with slope 2. When x is -1 and y is 1, I get a slope of 1 minus -1, or 2. So I'll sketch that in. When x is -2 and y is 0, I get a slope of 0 minus -2, or 2. So I'll sketch that in. Now moving on to x is -1, y is 2, I get a slope of 2 minus -1, or 3. So I sketch in a slope of 3. Same thing happens when x is -2 and y is 1, I'll get a slope of 3. And when x is -2, y is 2, +2, I get a slope of 4. So I sketch that in. So in doing that, I've created the direction field or slope field of the differential equation y prime equals y minus x. Now if instead I'm given a slope field, like here I've been given the slope field for the quantity y plus 1 times the quantity 2 minus y, I can look at different questions here, and the slope field's already provided to me. Now, in our first example, I could answer questions doing what I'm going to do in this example as well, now that I've created the slope field. We just had that extra step of having to create the slope field. But say, for example, that I'm curious how possible solution curves to this behave near the origin. So what I would do is I would plot a point at the origin, right there. And then what you do is you sketch a curve that follows the tangent lines as closely as possible. So it's looking pretty steep at 0, 0, and it's kind of, as we move to the right, it's getting less steep. And in fact, if I look at y equals 2, there seems to be some horizontal asymptote type of thing right here, where my slopes are coming down to it and going up to it. So as I move to the right with my x values, I'm going to go up and then begin approaching that horizontal asymptote value. And now if I look going to the left with my x values, it looks like they're getting less and less steep. And in fact, here again, at right about y equals -1, it looks like there's probably a horizontal asymptote happening that I'm getting closer and closer to from both above and below. So I'm actually going to have this approaching that horizontal asymptote as well without crossing it. So the sketch of a solution that might be close to the origin would look something like this. And I can notice that the solution, as x approaches infinity, the solution curve actually approaches 2. Y equals 2. Some people find creating direction fields or slope fields, that actual generation process, to be particularly tedious. I hope that you can embrace the simplicity of it and really appreciate that it's giving you this visual aid of what does this differential equation even look like? What do the solution curves look like for this differential equation? And appreciate the beauty that slope fields can bring you.